Welcome back to another recap video of JEE Mantra 2025 series. In today's session, we are going to discuss three chapters: atom, nuclei, semiconductor and electronic devices. Not to waste the time, moving to the very first chapter, that is atom. Here we are starting with Rutherford atom model. So alpha scattering experiment is not at all a part of discussion in today's session. We will be directly starting with Rutherford's observation based on that. Observation number 1. The entire positive charge was located at the center within a very small space of order 10 to the power minus 15, and that space he called it as what? Nucleus. That was observation number 1. Observation number 2 was, around this nucleus electrons are moving in circular orbit, okay, and they are what? Negatively charged, and altogether this negatively charged electrons plus the charge at the center of the atom, okay, which is positive, altogether gives net charge equal to 0. That means altogether the atom is neutral. And the fourth one, the most important thing, and this led to the the studies of the atom models ahead as well. The fourth one, the most important one, the force under the influence of which this electrons moving around the nucleus, that is because of the electrostatic force of attraction between the nucleus as well as the electrons moving around. That was the most important observations of Rutherford based on alpha scattering experiment. All right, so these 4 observations are very important. And moving to the next, there what we need to discuss about the closest distance of approach. The closest distance of approach means, if I am having an alpha particle moving towards an atom, okay, whose atomic number is Z. All right, so up to what distance it can reach? That means the closest distance approach, that means up to what distance they can come close to each other. That is what basically closest distance of approach. We calculate this based on law of conservation of energy. How will we calculate that? Initially, we will be considering the potential energy of the system, electrostatic potential energy of the system as 0, and it is going to have only kinetic energy, or kinetic energy of what? Kinetic energy of alpha particle. So this alpha particle's kinetic energy initial need to be the final potential energy of the system once this alpha particle is at its closest distance of approach towards the atom. Okay, so based on law of conservation of energy only we derive this particular expression, and the expression says the closest distance of approach is equal to R naught, isn't it? Here it is marked as R naught, that is equal to 1 divided by 4 pi epsilon naught into Z times E square into 2 all divided by E suffix k. And here E suffix k, what is E suffix k? I already told you, we do calculate this based on law of conservation of energy, and this E suffix k is the kinetic energy of alpha particle once they was at infinite distance of separation. All right, now moving to the next, that is impact parameter. Impact parameter means, if let this be the atom and let this be the nucleus, and here this is a line that I am creating which is passing through the center of the nucleus. Now here this is the alpha particle coming, and alpha particle once it reach within the electrostatic field, what will happen? It will be deviated. Now I can see this is the perpendicular distance of separation. Okay, I am marking it as what? B. Now this perpendicular distance of separation is known as what? Impact parameter, and the relation for impact parameter is small letter b, that is equal to 1 divided by 4 pi epsilon naught. Okay, 1 divided by 4 pi epsilon naught into Z times E square into cot of theta by 2 all divided by again kinetic energy, and here theta is the scattering angle. Okay, so these are 2 important mathematical relation. Relation number 1, that was about closest distance of approach, and second one was about impact parameter. Moving to the next, what was the limitations of Rutherford atom model? Limitation number 1, it couldn't explain the stability of atom, and limitation number 2, that was it failed to explain line spectra. All right, failed to explain the stability and failed to explain what? The line spectra. Moving to the next, that is Bohr atom model, we will be discussing that two important statements. Statement number 1, the angular momentum of electron moving around the nucleus, that is going to be what? Nh upon 2 pi. I repeat, statement number 1, that is angular momentum is Nh upon 2 pi. All right. Now, what is angular momentum? M into V into R, where M is mass, V is velocity, and R is the radius. Statement number 2. Statement number 2 says that these electrons, if an electron jump from higher level to lower level, if an electron jump from higher energy level to lower energy level, I mean higher radius of higher order to lower order, then only what? You can see, you can observe any radiations coming out from the atom. Otherwise, there will not be any radiations coming out from the atom. That means this particular these electrons which is moving in this orbit is going to have a fixed amount of energy. It's neither going to gain energy or it's not going to give up any amount of energy. And if it is happening, so that means if that energy is coming out in the form of photons, that means electron is jumping from higher energy level, okay, or orbit of higher order to lower order. It is. So that is statement number 2. Moving to the next, that is based on Bohr atom model, we need to discuss about radius, velocity, kinetic energy, potential energy, and total energy of electrons moving in any orbit. Okay, so the first one is about the radius. So if let this be the nucleus, and this is the first orbit, here this is the second one, and here this is the third one, so and so. Now, if you want to find out the radius of the very first orbit, then we have got the expression as 0.53 times 10 to power minus of 10, 0.53 Armstrong. That means here this is what? The radius of the very first orbit for a hydrogen atom. Okay, for a hydrogen atom. And the general expression is what? General expression is R is equal to 0.53 into n square by Z Armstrong. So here this is the general expression, and here this is for the hydrogen atom. Oh, and if n is equal to 1, I repeat, n is equal to 1, this value is going to be what? 1. And for hydrogen atom, this is going to be 1. And that's how we are getting it as 0.53 Armstrong. Okay, and as the orbit number increases, okay, first orbit, second order, third orbit, so obviously the value of n is going to change. And if we consider a hydrogen-like atom, then correspondingly you need to change the value of Z as well here. Moving to the next, that is velocity. The standard expression for velocity is 2.18 into 10 to the power 6 times Z by n. There it was n square by Z square, and here it is Z by n. Okay, and for kinetic energy, the expression is 13.6 times, I repeat, 13.6 times Z square by n square electron volt. 13.6 times Z square by n square electron volt, and it is kinetic energy, so you can see it's marked as positive. All right, and immediately connecting this, I want to take you to the expression of total energy. Here, in case of total energy, you can see it's negative of 13.6 times Z square by n square EV, electron volt. I repeat, negative of 13.6 times Z square by n square electron volt. So here you can see there is a relation between kinetic energy and total energy. Negative of kinetic energy is equal to total energy, or you can say that positive of, I mean here total energy is going to be negative, and if you eliminate this part, I mean whatever the value of total energy, the positive value of that is going to be the total kinetic energy. And what about the potential energy? Potential energy is going to be nothing. See here, this is total energy. Okay, exactly double of that. You can see this, it's minus of 27.2 Z square by n square times electron volt. So never get confused with these three terms: kinetic energy, potential energy, and total energy. Let's start with total energy first. It's going to be minus of 13.6 times Z squared by N square electron volt. And there it was minus, and if you remove that minus sign, you will get what? The total kinetic energy. Okay, and total energy multiplied by 2, that is going to be the potential energy. So potential energy as well as total energy is going to be negative, kinetic energy is going to be positive. What is the actual value of total energy? The positive value of that is going to be the kinetic energy, and the total energy multiplied by 2 is going to be the potential energy. So that is in short how we can explain all the energy values. And the next one is about the wavelength of the emitted radiations. I told you in the while explaining about the Bohr atom model, if the electrons jump from a higher energy level to lower energy level, there is the only possibility where we can observe radiations or photons coming out from an atom. Okay, and if those radiations are coming out, then what could be the wavelength of those radiations? Okay, that is at this point explaining about. So how to calculate the wavelength if such a transition is taking place is, the standard expression says it's going to be 1 by lambda times capital R into 1 minus N1 square minus 1 by N2 square, where capital R is known as Rydberg constant, which do have the value as 1.097 into 10 to power 7. Moving to the next, that is excitation energy and excitation potential. You must be very careful while listening to this particular segment. Excitation energy and excitation potential. The name itself says exciting. That means excitation energy, that is the energy need to be provided to any electron to excite it. That means to enhance the energy level, or you can say it's increase the energy level so that it can jump from lower energy level to higher energy level. That is excitation energy. And excitation potential, I repeat, excitation energy is the energy that need to be given to an electron which is at lower energy level to higher energy level, permitted higher energy level. All right. Now, excitation potential means it is that potential difference through which we need to accelerate these electrons so that it can attain excitation energy. Okay. So, excitation is just to take it from lower level to higher energy level. If you explain that in terms of energy, you may call it as excitation energy level. And if you want to explain the same in terms of the potential difference through which these electrons need to be accelerated so that they can attain that much amount of energy, then we call it as what? Excitation potential. All right. Now it has got an immediate, this particular content, this particular concept, this has got an immediate connection with the next, that is ionization potential and ionization energy. So excitation, if the higher energy level keep on increasing, that means it will go to infinity. But that means these electrons does not belong to that atom anymore. Now we may call this atom was what? Ionized. So ionization means what? Ionization energy means what? So ionization is, we are removing the electron from the atom forever. Then the atom got ionized. Now ionization energy means we need to provide a particular amount of energy to the electron so that it can be taken away from the atom forever. All right. So the final energy level, lower energy level is at where it is now, and the higher energy level is infinity. All right. So the energy need to be provided to any electron to remove electron from the lower, electron from where it is. Whatever the energy level, it do hold its position now to infinity. That is known as what? Ionization energy. And again, the potential difference through which this electron need to be accelerated so that it can be taken from the energy level where it is to the infinity. That is known as ionization potential. So it has both has very close connection. Try to understand that excitation and ionization. Ionization is basically another version of excitation only. The only difference is that the higher energy level is infinity. That is the only difference. All right. Next is ionization energy and ionization potential mathematical expression. So I told you here the higher energy level is infinity. So here you can see N2 is infinity. All right. N1 is taken as N. So you may have the expression for ionization energy as what? 13.6. I repeat again, 13.6 Z square by N square electron volt. This is the energy what we are providing. So that's, it's positive now. Ionization potential definitely what will appear there? An extra E term is going to be there. all right, in the denominator. So the final expression is going to be 13.6 z square by n square times only. Fine. So that E term is going to be missing over there, because what? It is potential difference that we are applying. So energy divided by the charge, this is work upon charge is potential difference. So we will be dividing this by E term, so that E term will cancel each other, and you are going to get the expression as minus of 13.6 z square by n square volt. Okay, so here I repeat once again, ionization potential is positive, ionization potential difference, ionization energy is going to be positive, as well as ionization potential is also going to be positive. In this case, that negative cases, that negative value does not hold any significance here. All right, moving to the next, that is de Broglie wavelength of an electron. So basically what this tells about is, see here, this is the nucleus and the electrons are moving like this. So for an electron moving like this, so since it do have a non-zero value of linear momentum, so there will be a wavelength associated to this, and that wavelength need to be what? H by P. De Broglie wavelength, that need to be what? H by P. And what is P here? P is M into V. All right. So if I consider this entire track, okay, that's going to be what? The perimeter of radius small letter r. So 2 pi r is going to be what? N times lambda, and that is going to be n into, what is the expression for lambda? That is h by p. So the final expression is nh upon, instead of p, what we have? M into v. So this is that particular expression. So that is the wavelength of an electron moving in the nth orbit. Wavelength means wavelength of de Broglie wave associated to electron. All right, moving to the next, that is hydrogen spectrum. So if, let this be the hydrogen atom and here be the electron, by any means, if this electron get excited to higher energy level, that means here this is orbit number 1, orbit number 2, orbit number 3, orbit number 4, like this. Okay, so if this electron excite from lower energy level to higher energy level by absorbing energy, so at higher energy level this is not at all stable, so definitely it need to come back to the ground state, isn't it? So it completely depends what was the energy provided, isn't it? What was the, definitely point number 1 is what was the amount of energy that we provided, that matters a lot, up to what higher energy level that is going to jump from the ground state. Now this is at ground state, now it need to come back to its original position. So while coming back, matter number 1 is what is the higher energy level and how it is coming back, whether it is directly coming from the higher energy level directly to the ground state, or step by step it's trying to reduce its energy value. It matters. So based on that, radiations coming out from the atom also will be different. So if we collect the entire radiations and if we classify that into a group, we can have a series over here. First one is Lyman series, next one is Balmer series, Paschen series, Brackett series, and Pfund series. Okay, now how they are different? In Lyman series, the electrons are jumping from higher energy level 2, 3, 4, 5, etc. to lower energy level, that is 1. Okay, and this particular series will be giving radiations of spectrum ultraviolet. Okay, that means in the electromagnetic spectrum their position is going to be in the ultraviolet region. Next one, Balmer series. Here the electrons will be jumping to level number 2 from higher energy level 3, 4, 5, etc. And this in the electromagnetic spectrum, this particular series belongs to visible region. Next is Paschen series. Here the electrons will be jumping to orbit number 3. I repeat, orbit number 3 from 4, 5, 6, etc. And again this belongs to infrared region. Brackett series, here the electrons are jumping to level number 4 from 5, 6, etc. And again this belongs to infrared region. And the last one is Pfund series. Here the electrons are jumping to level number 5 from level 6, 7, etc. And again, this belongs to infrared region. All right. Now, let me take you to the next chapter, that is nuclei. All right. Here, first we will be discussing some important terms. Out of that, the first one is atomic number. It's number of proton. Next is mass number. That is number of proton plus number of neutron. The nuclear size, basically they are asking for the radius. That's going to be R equal to R naught a to the power 1 by 3, where A naught is going to be 1.1 into 10 to the power minus 15. Next is nuclear density. Basically, it's the density of the nucleus. That's going to be the mass of the nucleus by its total volume. And you may have the expression as rho equals 3 times m all divided by 4 pi into R naught cube. Okay, and here you must understand one thing. This particular density does not depend on the mass number. It does not depend on mass number. So nuclear density, the density of the nuclei is always a constant. It does not depend on mass number. All right, and moving to the next, that is atomic mass unit. Atomic mass unit is, unit what that we use to represent the mass of nucleus and nucleons. Okay, and one atomic mass unit is basically 1 by 12th mass of carbon 12 atom nucleus. Fine, and that is approximately equal to 1.6 into 10 to the power minus of 27 kg. And if you want to represent in terms of its energy equivalence, you may have it as 931 mega electron volt. Okay, next is isotopes, isobars, isotones, and isomers. Isotopes means is going to have the same atomic number and different mass number. Okay, and isotopes is atoms of same element. I repeat, atoms of same element having same atomic number but different mass number. Okay, so isotopes, same atomic number, that means same number of protons. Okay, then isobars, reverse of this. Okay, and the difference is it is of different elements. It's of different element having same mass number. There it was what? Same atomic number, isn't it? And here it is same mass number but different atomic number. All right, so atomic number is different. That means the element got changed. Fine. Now isotones. Here isotones, the number of neutrons, isotons, n is there. Number of neutrons is going to be the same. So same number of neutrons but different atomic number and mass number. All right. Next is isomers. They are having same mass number and atomic number, but there is a difference in the energy state, or you may say that they are having different radioactive property. Okay, next is nuclear force. Okay, regarding nuclear force, you need to understand these points. Point number 1, the strongest force in the nature. It's short range force. It's non-central and non-conservative force. It is charge independent, and while comparing with electrostatic force, it is 100 times stronger, and while comparing with gravitational force, it is 10 to the power 38 times stronger, and it is believed to happen as a result of exchange of particles, which is known as meson particles. Important point regarding nuclear force. Okay, fine. So concept based questions if comes and match the following and all, then assertion reason types questions, this information might be very helpful for you. And moving to the next, that is mass defect. As the name says, it's a defect associated with the mass. So basically mass defect means it's the difference between the mass of the nucleons as well as the mass of the nucleus. We represent it as delta m. So delta m is, here this is mass of nucleons and here this is mass of nucleus. So difference of that is what? Delta m. Okay, and if we take the energy equivalent of delta m, that is delta mc squared, that is what we call it as the binding energy, and binding energy per nucleon means binding energy upon the number of nucleons, that is basically the mass number. So the next topic is packing fraction. All right, packing fraction is a very important information regarding the stability of nucleus is concerned. So basically packing fraction says F equals mass of the nucleus minus mass number upon mass number. All right. So greater the value of packing fraction, greater is the stability, and that is a very important information. Now moving to the next, that is binding energy curve. In this binding energy curve, we need to understand basic points. Point number 1. If the mass number is between 50 to 80, for those nucleus whose mass number is between 50 to 80, they are the most stable nuclei. Okay. Next, for mass number greater than 80, the binding energy per nucleon decreases, and beyond BI 83209, okay, it is what? Radioactive, and the nuclei which is having mass number less than 20, mass number less than 20, they are comparatively unstable. All right. So these are the 4 important points associated to the binding energy curve. All right. What are they? If the mass number is between 50 to 80, they are the most stable. And if the mass number is greater than 80, all right, the binding energy per nucleon gradually decreases. And beyond this limit, BI 83209, it is going to be a radioactive nuclei. And if the mass number is less than 20, again, there is a comparatively instability will be there. All right. Moving to the next, that is Q value. Okay. So Q value is if there is an energy difference, if there is a mass difference between the constituent particles before a nuclear reaction and after nuclear reaction. That means the mass before the nuclear reaction is a different value and mass after the nuclear reaction is a different value. That means there is a difference in the mass, and the energy equivalence of that mass is basically, we call it as what? Q value. Okay. And what are that nuclear reactions? What are the classifications? There are basically 2 types of nuclear reactions. First one is nuclear fission reaction, and next one is nuclear fusion reaction. So nuclear fission reaction is the case where a nucleus split into 2 or more than 2 lighter nuclei. Okay, so here you can see uranium is hit by neutron, that gives barium and krypton. All right, and byproducts are 3 neutrons plus some energy. See, this is that Q value. Okay, and that is equal to the mass difference, that is delta M, into C square. That means the energy equivalence of that mass difference. Next category is nuclear fusion reaction. So here lighter nuclei combine to give a heavy nuclei, okay, heavy nucleus, and byproducts you can see here. All right, and again Q value is there. That means energy is released. Again, energy is just because of that mass difference only. All right, and here we move to our 3rd chapter, that is electronic devices. Okay, now in electronic device, the first thing we are going to discuss is about energy band, valence band, conduction band, and forbidden energy gap. So energy band, basically it's collection of closely spaced energy levels. So it's basically telling about the energy levels. Okay, and next is valence band. Valence band is what? The energy band that contains valence electron. That means that positions where we can identify the energy level of valence electron. That altogether gives in a region. All right, and that region is what we call it as valence band. Similarly, if we identify the electrons in conduction band and if we spot the energy level in the energy band diagram, then that energy band is going to be what? Conduction band. Okay, now if definitely conduction band means is going to have higher energy level. So here these are, that means all the conducting electrons. All right, conducting electrons or free electrons we can say, its positions is like this. That means here this is the lowest position and here this is the highest position, and here this is the valence band. and here this is conduction band. So here this is the maximum value of valence band, and here this is the minimum value of conduction band, and the energy gap between this is what we call it as what? Forbidden energy gap. Okay, for semiconductor germanium it's going to be 0.72 electron volt, and for silicon it is 1.1 electron volt. All right, moving to the next, that is how we can classify the material into conductor, semiconductor as well as insulators based on energy band diagram. All right, in case of conductors, the energy band forbidden energy gap, that's going to be very less, or either it will be overlap. Okay, and for insulators, it's going to be very high. For insulator is going to be very high, and for semiconductors the gap will be less than insulators and greater than that of conductors. The next is types of semiconductors. We can have two types of semiconductors. The semiconductor in its pure form, we call it as intrinsic semiconductor, and the one in its impure form, that means if we add some dopants, that is known as extrinsic semiconductor. So the type of the impurity that we add, precisely saying whether it is a trivalent or pentavalent impurity, we may classify that it as N type as well as P type. Here this is for trivalent, and here this is for pentavalent. All right, now if a semiconductor, intrinsic semiconductor got converted into an extrinsic semiconductor, then the charge carriers, the density of the charge carrier, so the charge carrier available per unit volume, the general expression is Ne. Ne is the density of electrons, NH is density of hole. So the intrinsic semiconductor as well as extrinsic semiconductor, once the impurities are being added, then we may have the expression as Ne into NH equals Ni square. All right, and what about the current? Current is current due to electron plus current due to the holes. All right, next one is about the conductivity as well as resistivity. Okay, the general expression for conductivity sigma is going to be Ne, that means density of electrons multiplied by E, that is charge of electron, multiplied by mobility of electron, plus NH, density of hole, multiplied by E, charge of electron, multiplied by mobility of hole, and that is equal to 1 by rho, where rho stands for resistivity. Moving to the next, that is important terms. Okay, first one is depletion layer. It is that particular region at the p-n junction where there is no charge carriers. Okay, next is potential barrier, potential difference across the depletion region. Third one is forward biasing and reverse biasing. So if I have got p-n junction like this, here this is the depletion region. If I connect this to positive and this to negative, this is known as forward biasing. And if again this is the depletion region, here this is p region and here this is n region. If I connect this to negative and this to positive, then this is known as what? Reverse biasing. So here this is forward biasing and here this is reverse biasing. Okay, next is VI characteristics of forward biasing. We all know that if we have a p-n junction like this, p region, n region, and if we apply a potential difference like this, until or unless the external battery EMF offered by the external battery is greater than the barrier potential, there won't be any flow of current, and after that there will be flow of current. That is why you can see the graph like till that difference creates, I mean the applied potential difference is greater than the barrier potential, there won't be any flow of current, and after that the current can increase like this. So here this is I and here this is V. Okay, and so here this is the VI characteristics of forward biased circuit of across a p-n junction. All right, and here this is reverse biased condition. So reverse biasing, you know that basically we are connecting voltage. Here this is p region, here this is n region, p-n junction, and negative voltage. All right. So if we keep on increasing the voltage, the thickness of the depletion layer keep on increasing, and once the voltage, I mean the potential difference cross beyond a limit, what will happen? There will be a movement of minority charge carriers. Okay, and that particular voltage is known as what? Breakdown voltage. So the graph is going to be like this, and at breakdown, what will happen? Suddenly there will be a flow of current, and this is because of minority charge carriers. So you must understand that point as well. All right, so here this is VI characteristics of reverse biased PN junction, and here this is of forward biased PN junction. Moving to the next, that is half wave rectifier, and in the next we will be having full wave rectifier as well. So here let me discuss the half wave rectifier first. So in case of the half wave rectifier, so basically what is the purpose of rectifier? Rectifier converts AC signals to DC signal. That is the main purpose. All right. So half wave rectifier, as the name indicates, it will be converting half of the input signal only. And full wave rectifier, that will be converting the entire signal part. That means upper half as well as lower half will be converted in full wave rectifier, and sorry, and in half wave rectifier only half part will be converted. So here you can see a PN junction connected across here. So here this is the transformer arrangement. That means this pass on the input to the next circuit, and here I am having the diode. All right, and here this is the output. So for the first half, this is going to be positive. Here so it's going to be positive. So here this is going to be positive, again this is going to be positive. That means here this will conduct the current. That means signal will be appearing. The next half cycle, this is going to be reverse bias condition. That means it won't be identifying that current. The next half it will identify, in the next half it won't identify. So you are going to get an output like this. This is the way we call it as what? Half wave rectifier. But in case of full wave rectifier, we are having two diodes. All right, we are having two diodes. So basically what happens over here is, for the first half, if this is forward bias, then this is reverse bias. In the second half, this is going to be in reverse bias condition, and here this is going to be in forward bias condition. So in both the case, what happens is the output will be appearing across the terminal here. That means we will be getting the upper half as well as lower half. That means the output will be identifying the upper half as well as lower half, and you are going to have an output waveform like this for an input wave shown in the figure. Okay, the next is Zener diode. Basically the purpose of this is, this arrangement act as a voltage regulator. All right, that means if I have got a volt setup like this, okay, and let this be a device which need to be worked under a particular voltage. Okay, and here this is a basic circuit diagram. Okay, and understand one thing, Zener diode work on reverse biased condition only. Okay, now if we keep on increasing the voltage across here, okay, until the breakdown voltage doesn't reach, this is not going to conduct any current, isn't it? Because this is in reverse biased condition, so the current will be flowing like this. Once the applied voltage is greater than the breakdown voltage, there is, as per the graph, there is an immediate current flow through the Zener diode. That means there will be current flow through this Zener diode. Okay, and what happens, you know that the voltage across this is always the Zener voltage. I mean, as per the graph, this is going to the voltage across this arrangement. So if the voltage across this arrangement is fixed, the device which is connected across the Zener diode is always going to receive that potential difference only. Now whatever the additional potential difference, that whatever the additional EMF that we applied over here, that will appear across this resistor as V suffix R. Okay, so the EMF E, that is EMF of the voltage, is going to be the voltage drop across the resistor plus Vz, where Vz stands for the breakdown voltage. So this device will be either having Vz value or a voltage value less than that. So the device is safe. Okay, so this is how it works, like a voltage regulator. Fine. Next is LED. Fine. So if we provide energy to electron, that will jump from lower energy level to higher energy level, isn't it? And if electron come back to its original position, then what has to be there? Radiations has to be given out. That means energy need to be released. So by absorbing energy, the electrons is moving out from its space, and if it is coming back to its original position, what happens? Energy will be released. That is a in short working behind what? Zener diode. And this, sorry, not Zener diode, LED. And this LED circuit work under forward bias conditions. So the graph of LED you can exactly see as the forward VI characteristics of a forward PN junction only. All right, and this is the basic symbol for LED. Next one is photodiodes. The purpose of photodiode is to identify light signals. I repeat, to identify light signal. Its purpose is not to create any electrical energy. So again, the photodiode, as the Zener diode was working under reversed bias condition, photodiode also will be working under reversed bias condition only. So the variation of the graph, you can see exactly the replica of reverse VI characteristics of a reverse biased PN junction, and here this is the symbolic representation for that. Moving to the next, that is a solar cell. So here this particular arrangement is used to convert light energy into electrical energy. All right, the symbol is this and the graphical representation is this one. And here regarding the graphical representation, you must understand one thing. Here this is I, if I take this as I as well as this as V, here this is open circuit voltage, and here this is short circuit current. All right, and moving to the next, that is logic gates. Basically logic gates is the electronic circuit that works on certain conditions. For example, if we are moving towards the door of a shopping mall or any hotel, something like that, once we are approaching the door, you can see that it opens. Okay, and if no one is coming, then it will be closed. So there is a condition. If somebody is coming, that is a condition. If somebody is coming, that is the condition. Then the current need to be supplied to the motor that controls the gate. And if no one is coming, no movement is there between a particular region, that means there need not be any current flow towards the motor. All right, so that is a condition. So how to understand that condition and how to control the flow of current based on the condition, there lies the importance of logic gates. Basically, we have got three fundamental logic gates. All right, and the logic gates are, first one is OR gate, next one is AND gate, and third one is NOT gate. All right, so let's see what is OR gate. So here, this is how we represent an OR gate. It's having two inputs, A as well as B, and one output, that is C. Okay, and if this is A, here this is B, and here this is C, I may have four combination, that is 0 0 0 1 1 0 1 1. For OR gates, A or B, if A or B is 1, then output is going to be 1. I repeat, if A or B is 1, output is going to be 1. So here it is 0 0, here it's going to be 0 0 1, we have got B as 0. I repeat, A or B is 1, output is going to be 1. So here also it is 1 and here also it is 1. But here in case of AND gate, here we need both A and B. I repeat, both A and B to be positive. I mean positive in the sense 1. All right, it's basically a signal is there or not, that is a condition. If condition is yes, that stands for 1, and if the condition is no, that stands for 0. So in somebody used to say it as positive, somebody used to say it as 1, okay, or negative for 0, like it's a basic coding language. Then so for AND gate, as I said, A, B, C, A and B are the input and C is the output. 0, 0, combination is 0, 0, 0, 1, 1, 0, 1, 1. We need A and B. I repeat, A and B as 1 only. So here 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. A and B. So here this is the only case where A and B is 1. Therefore output is going to be 1. On rest all case it's going to be 0. Next is NOT gate. NOT gate means there, I missed the symbol here. So here this is the symbol. Here this is A, here this is B and the output is C. Okay. So OR, this was for OR gate. Okay. Starting with an opening of O and input is there. And AND gate, D is there. D is there. This is how we can connect the symbols. Alright. And for NOT gate, we are having only one input A and only one output C. That means if the input is A and B, so the possibilities are only two, isn't it? Either it could be 0 or it could be 1. If it is 0, it's going to be 1. And if it is 1, it's going to be 0. That means whatever the input is, just opposite is going to be the output. Okay. Now the combination of NOT and OR. I repeat, OR gate followed by a NOT gate. A, B. So here A, B, C was the truth table combination for the OR gate. So it was 0, 0, 0, 1, 1, 0, 1, 1. Output is 0, 1, 1, 1. Once we have got a NOT gate connected across, I mean in the output terminal of that OR gate. So here is going to be what? 1, 0, 0, 0. So here this is going to be the truth table for what? NOR gate. Truth table is what? Truth table is the table that tells about the possible output combination for different value of input. So here this is the truth table for OR gate. Here this is the truth table for AND gate. Here this is the truth table for NOT gate, and here this is the truth table for NOR gate, and comes the last, that is NAND gate. Again A, B, C and C dash. Okay, 1, 2, 3, 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, isn't it? Here it is 0, here also 0, it was 1. And C bar means here this is 1, 1, 1, 0. And the symbolic representative of this one is what? This is AND gate and here this is NOT gate. And if it is represented like this, that is also what? NOT gate only. And similarly, here this was OR gate. Okay, and if there is a bubble here, this also represent what? Your NOR gate. Alright, that was all from the recap video for this session. We will meet soon with the detailed discussion of another chapters. Till then, bye and take care.